All right, folks, welcome back. The topic that I'm going to talk about today, or the paper, is an interesting paper, one of the few that I have seen, which talks about recognizing scene text that is in very non-standard forms. These non-standard forms of text are much more common than you think. For example, the way Sachin asked, Sachin, this literally goes to your question. Suppose you see the word on a scene written like this, on a logo or something, coffee, right? How would you recognize this text? And there are not that many papers or works that I found, or models that do a good job of it. This one is pretty good. So the point the author makes is that the conventional approaches don't work. What are the conventional approaches? If you try to do a text detection as a object detection problem, and you make a rectangular bounding box, you realize that this bounding box, look at this one, A, is quite imperfect, isn't it? Because it has some part of the image, picture, etc. at the top of it. The word coffee is in a curve. Then people try to improve upon that approach using approach B, which was, it said, okay, let's tilt the rectangle, right? First, figure out what is the angle of the rectangle, and we'll work with that. It's an improvement upon the first approach. When you tilt the rectangle, well, something is better, but still not quite okay, right? Then you can say, well, we won't use a rectangle. Let's use a sort of a, what is this thing called? Quadrangle, right? Or a trapezoid, quadrangle here, or something like that. And when you do that, now you're more flexible about the heights in the two places. Quadrangles are good when you want to capture linear perspective, you know? For example, if you're looking at the side of a building and the building goes, you realize that this height near is more than the height that is far. So anything that is written here shrinks in size. It's called linear perspective. So obviously this sort of quadrangles work pretty good in those situations. A simple example of linear perspective is when you walk through an avenue of trees or an avenue of light poles, you do notice that the poles, they begin to get smaller in the distance, right? So for such situation, this might be better. But at the end of the day, none of these methods are as good. And what they propose is an interesting method, which makes a beautiful geometric argument. It says that, see, let us do one thing. Let us recognize a local area that we know is text, right? You call it a text region. A text region, and then it does something better. So that is the blue part. So it discovers a lot of these circular text regions, sort of. And then it says, let us also try to discover something that if you look very carefully, you will see a green line going through. Do you see? I'll just exaggerate the green line. The green line going through the center of the text. You see that, guys, isn't it? Right. So it says that let's also discover the text center line. So two things: discover where the text is and discover the center, the core line going through the text. That will be a curve. Actually, line is not the right word. It's more like a curve. Make sense, guys? It's a curve. You find that going through the text. So the two things that you try to discover is text region and text center line. You will see references in this paper to these two things, text region and text center line. So what are they focusing on first? They're focusing on text detection and understanding of it. So let's just look at it more carefully. So they point out that all the related works don't work. Here is their methodology. And you first find the regions of text. And how do you do that? So ignore this picture for now. This has to be run a little bit backwards to read this paper. Look at this picture, guys. I'll exaggerate the picture a little bit. And so what you do is you use some sort of a network, and I'll talk about what that network is. Do you see those mysterious words, FCN plus FPN? How many of you, by the way, read this paper? So FCN is fully convolutional network, and FPN stands for feature pyramid network. So once again, they're using two different networks, putting them together. But what do they mean by that? I'll explain in a moment. You know what a convolutional network is. You do a lot of feature map extractions. But then when you want to classify it as a cat or a dog, what do? You feed it into a feed-forward network to produce a single vector out of it, which you feed into a softmax, isn't it? So there is always a dense layer or a feed-forward layer at the tail end of it. The tail is made up of, right? And what these people say a fully convolutional network is in which you have chopped off the linear layers or the dense layers or the feed-forward layers, whatever word you want to use for it. You throw away the classifiers, the softmax, you throw away the feed-forward layers. The only thing you keep are the convolutional layers. So what is a convolutional layer made up of? Convolutional filters and pooling, min pooling, average pooling, max pooling, whatever. One layer is made up of these two operations, isn't it? That is it. So you keep only that. So you will get a fully convolutional network. And then there is something called a feature pyramid network. That refers to a very important paper, which we haven't covered, but this is a good occasion for me to talk about that very interesting conceptual development in computer vision. But what they are saying is, we are going to jointly learn 5 things. Make the network predict 5 things simultaneously. First is TR. And now remind us, what was TR? TR was text region. Remember, we just did it, right? I just said that a little while ago. I said that we will use the word TR for text region, isn't it? So we do that and observe the first picture carefully. Look at this picture. If you focus on this picture, and this is your reference, do you think it's doing a good job of predicting where the text is? Isn't it? So it has entirely rejected the hen in the center, right? The hen has disappeared. Only the text region. So the deep red represents the regions of high probability that it's a text region. Blue is low probability that it's a text region, close to 0 probability that's a text region. So you can see that the red areas are where the texts are. It does a pretty good job. And in fact, this is one area where the convolutional thinking shines a lot. Right? It does a very good job. The second thing, the feature that you learn from it is a text center line. So where is the text center line? The text center line is, where is it? Oh, sorry. Let me take this. Would you agree that this is the text center lines? Does it look reasonable, guys? Yeah. And is this what this picture is looking like? Right? But you notice that in the text center line image, there is a bit of a problem because it's getting confounded by even this hen. You see some of the hen showing up, right? The hen is not marked as red, but it's beginning to wonder, is that text too? Is it the text center line? right? And so they had an idea. They said, well, what if we superimpose TR on top of this? So wherever, unless they both match, don't consider it a center line, right? So what will happen to this? Look at, that is the masked CCL. What happens? Wherever the TR says there is no text, ignore those regions. So then you get a clean masked text center line, right? So it's a derivative product of these two discoveries, these two feature discoveries. And then what it says is, imagine that through this text is a, let's say that you have P written, then around the P or somewhere around this, you can wrap it up in a circle. This P is relative to the horizontal at an angle theta, isn't it? And so you can infer many things. You can infer the radius of the text there, right? You can tell the theta, and most importantly, you have to tell where is the center in the image, what's the coordinates of the center of that circle. Are we making sense, guys? Right? So that is the radius. Now, cosine theta and the sine theta, it finds out for each of these places. For some reason, they do both, not just theta. They must have realized that it's a good way of doing it. I thought about it, why it could be. Just off that, I think it's because what you really need is theta. Theta is the tan inverse of slope, right? Basically. And so what you need is sine theta, tan theta to know the cosine theta to know the slope, right? The tilt. Theta is a measure of the tilt, basically, slope. And so you need this, right? So that is one way I looked at it. But anyway, if you have a better way to think through it, let me know. I may be wrong. Now, once you discover these things in this paper, then the rest of it begins to look a little simpler, isn't it? What you can do is, and the main technique is, and I'll explain. So ignore this picture of what it does, okay? Because I'll come to it in an iterative way. See, they use a complicated algorithm of imposing circles upon the text region, right? You know the center line of the text, right? You have the center line of the text. Let's say in this particular case, actually they changed the example. In this case, it is like a bowl shaped, right? Curve shaped. But they take another example, and that's what may confuse you. So imagine that the text is this. And so this is how the text center line will look, isn't it, guys? So what it says is, go take an arbitrary point on the text center line. And then what you can do is, on that point, you can then move away from the point, little bit, stride away, one stride to the left, one stride to the right. And how? First, given this point, you can find the tangent plane, the tangent line of the curve. Those things, by the way, in computer vision are well established, right? And so you make one step in this direction, one step in this direction. Once you do that, right, then again recenter it. Like, why? In the vicinity will be a point. So suppose you took this point. Let me take a white colored so that I can make the ideas clear. This one. So suppose you took this point. Oh goodness, that's fat. But you ended up with this and this. What can you do? You can center it, bring it down to the center line, peak of the probability, right? Bring it back to the center line. So then you will end up with two more points, these 2 points, these 2 points rather. These 2 points will gravitate and become these 2 points. Like once you bring them to the nearest center line point, you take one stride in opposite directions and then you drift towards the center, maximum peak. So you do this. And if you keep striding this, then dot, 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 dot. You will end up with this curve. Make sense? Right. You'll end up with this curve. So this striding, reconstruct by slicing a circle along the center. So now what can you do?
As a question. So this concept does work for other shapes?
Every shape.
Okay.
Because it uses, see, the point is that it all comes from the fact that locally you're making order 1 changes, right? You're drifting just a little bit. Yeah. So however complicated it is, all it means is that you look in a very tiny local region and everything looks relatively flat, isn't it? Another way of saying it is that everything can be thought of as the word people use, and we use the word manifold, that on any manifold, local patches look flat. Right? So you can do that. Now, so from this, what they do is that you can start drawing circles around it. All these points, draw circles, but draw circles in such a way, this circle, for example, that at least half the area of the circle is covered by the region, text region, right? Don't make too wide a circle. So make the circle like this. And now all you have to do is, once you have this circle, you have a series of circles, right? And so you can say that logically your text, whatever the text is, right? It is basically the sequence of text is nothing but these circles. Let me just call it disks, D1, dk. It is a set of disks. To read the text or the sequence of tokens is equivalent to reading what is inside the disks. Right now, there is some more geometric arguments it makes and so forth. I won't go into it, but let's look at this problem. What they're saying is, and then I'll go into the network architecture. They're saying that this is made up of a loss function, that is a classifier loss and a regression loss. What does a classifier loss do? What is classification? Let's go back to this problem, this picture, and try to figure out what is classification. When we want to discover the feature text region, is it a classification or regression problem? Are we finding for each pixel there, are we finding out the probability that it's a text? Isn't it? We are trying to tell whether it's a text region or a non-text region, non-text pixel.
Yes.
That's a classification. So this guy contributes to a classification loss. Right? Likewise, this guy contributes to a center line also. Is it a center line point or not? These top two contribute to a classification loss problem. What about the radius, cosine, and sine? Those are numbers. We are trying to predict how wide is the radius. So for example, you notice that this is red and blue. It means that the text here is really big. Bright blue means text is there, and much smaller text is in the curved face. Yeah. We are trying to do the radius. So the radius estimation is pretty good, but radius is a what? A number, right? So it's a regression loss problem. So this will contribute to these three things: radius, cosine, and sine will contribute to a regression loss. So what you're doing is you're saying that the total loss that you will train the machine on is made up of the classifier loss and the regression loss. Obviously, the classifier loss is made up of which two terms? The loss associated with learning the text regions plus the loss associated with learning the text center line, right? And the regression loss, as we just noticed, is made up of the radius plus L of the cosine theta plus L of the sine theta, right? It's the common sense, literally, just looking at it. And what they're saying is that you can minimize the joint loss. But when they do that, they realize, and let me just go down to that. And then, so this paper is very interesting. You have to sort of not read it in the linear way unless you know what you're looking for. But you have to read it in the way you would logically think about it. So you notice that they are doing this. They're saying that the classifier loss is lambda 1, lambda 2. Well, they're saying how much importance should I give to region versus center line, etc. But as they find out, what really works is all the lambdas is equal to 1. Means forget the lambdas. Right? When you forget the lambdas, it becomes what we just wrote. Right. Now comes the question. Okay, this is very good, but how do we did that? How did it? And so when you look at the way it works, do you notice how beautifully it works? You can have text in any shape. They call it the text snake because a snake can be any shaped snake, right? So you can have a text in any shape and it will detect it, right? Now comes the question, how would you do that? And obviously there are benchmarks saying they're very good performance and this and that. So there are two core ideas that you use. One is, do you remember this actually uses papers that we have covered. How many of you remember the UNet paper? Right, for segmentation and masking. What was the UNet paper? You would convolute, you would downsample, get this hidden representation, and then you would upsample, deconvolute, upsample. But at each point, you created a residual connection. Right? So not only, let's say that this is A, to go from A to B, right? You not only used, let me use B tilde, you not only deconvoluted or A to get a bigger picture and use that information, but you also took a bit of the original B, which was on the journey down, and you use that together to reconstruct, or the super resolution kind of activity, upsample it. Now, why did UNets work well? If you remember, it worked well because the features give you local information, whereas the original picture has a more global information, context, right? So you have both the feature and its context. So UNet, as we recall, is an extremely successful architecture that's widely used even today. So they will take the idea of UNet, and you'll see why, because it is sandwiched. So UNet is your CNN. The convolutional part comes from the UNet part, right? And then they use the argument of something called feature pyramid network, which captures a very simple thing. Let's say that you have an image, cat. You create the first convolutional layer, the feature map will be smaller, isn't it? So suppose this is, let's take an example, 512 by 512 pixel. Maybe the first set of feature maps will be only 64 by 64 or 128 by 128, whatever it is, right? 256, choose, pick your number. You're downscaling at each stage, but the number of features are increasing. You're using more filters, right? Now what happens is, sometimes more information is there in the more global picture, right? So for example, to tell that something is a person versus a house, maybe all you need to know is this versus this, right? So when you create feature pyramid, let's say, this is the intuition I carry in my mind. When you create a feature pyramid, keep on at each stage of the CNN, what does it do? It creates smaller and smaller feature maps. They contain more higher level abstractions. I call them, at the top you have stick figures, right? If you're telling a person from a house, maybe the top level is probably more predictive of what it is, isn't it? It is enough to tell broadly what it is. Maybe knowing every single feature of this kid and the clothes he wears and everything is just distraction, right? Because who knows, the top of the house or the wall of the house might begin to look like somebody's dress, right? On the other hand, if you want to tell between two brothers, you need these details. So sometimes it's the outline and sometimes the details. In other words, higher level features or initial features. So what feature pyramid network says is that you take all of these, you make a prediction from this level, 0, prediction from level 1, you make each of them predict. Let's say this is level K. Each of them predict, is it a house or a boy, or whatever problem you're solving, right? And use a composite, sort of like an ensemble of these predictions. And when you do that, whatever the correct resolution is at which the prediction should come out, that one will dominate very clearly with a high probability. Others will say, I'm not sure. You're getting the idea, right? I'm not so sure. As sure as this guy, isn't it? So that's the idea of a feature pyramid network. That's all it is. So in a feature pyramid network, once again, what you do, you take this CNN, you chop off the feed-forward path, the end, dense layers at the end. You just keep the feature pyramid. You just keep the convolutional layer to create the feature pyramid. That is why you realize why in this they started out. So now let's go back and read the paper and it will all make sense. They say that they use the idea of this. So guys, this idea you understood, right? That any text can be captured by a series of disks in a snake form, right? Then now you understand why we are talking about FCN and FPN, fully convolutional network and feature pyramid network, putting the ideas together of that, right? And basically it's a unit. If you look at this, what does a unit do? A unit, at each pair, it goes and informs, helps in the construction of the upscaling journey also, right? Each downscaling convolutional layer or feature map also leads to the reconstruction part, feeds into the reconstruction part, isn't it? So that is what is happening. You take an image, you will get a feature map, lots of features, F1. Then you convolute again, you'll get F2. You convolute again, you'll get F3. Convolute again, you get F4. And convolute again, you get F5. You treat, well, 5 layers. They say, okay, now enough. This is our hidden state, right? Now comes the part. What if I deconvolute it? This hidden state, if you deconvolute, you will get something of the size produced by F4, isn't it? Because now deconvoluting, you're upscaling. Yeah. So if they are of the same size, then you can add up. You can take, this is your unit thing. You see that the unit argument, you're feeding in some of the original signals, feature map, into the deconvolution journey, right? So this is the unit if you just look at it in this form, horizontally laid out, right? Typically you think of unit like this in the typical picture. Here it is laid out like this. Then once again, you bring these two together. So add it up, deconvolute, add the next signal, deconvolute, add the next signal, and so on and so forth, and finally make the prediction, right? So you're basically putting unit together with the notions of feature pyramid map, right? Feature pyramids network. That's all it is. And so what they did is they just took a VGG. In those days, VGG and ResNets were the state of the art. And they did that with great results. And that is it. There is nothing else in this paper, actually. Once you get that much, the small details. And as you can see, the important thing with this paper was that, see, it's very interesting that this didn't get noticed because I suppose the use cases where people use it at industrial scale, there are very few companies and so forth. But if you look at the benchmark, it is the most remarkable benchmark. Do you realize that precision has gone up by close to 40, 50 points? Like, that is like huge. It makes an improvement upon the state of the art by huge margins, shockingly high margins. It basically means that the old approaches were relatively junk, isn't it? And actually, this is used in production quite a bit, right? Likewise, you look at this other quantitative metric, where it goes up by a huge, huge amount, right? All these benchmarks, right? It sometimes it wins, sometimes it doesn't. But when you have long straight line text, what is surprising is that even when the text is straight line, it seems to be doing well, which is a little hard to understand why, but it does well, not by a wide margin. But whenever there's a curve in the data, there is almost no doubt that it does well by a wide margin, right? So this is it. This was your TextSnake paper. Was it fun, guys? The idea, you see how well it is thought through. Remember, this is the pre-transformer world, right? So we'll again take a 5-minute break, and please no more than 5 minutes, guys. And then we'll do the last paper reading. Then we'll start the presentations. Sachin, are you ready with your presentation? I think Sachin's team was the first one, right? And Albert, your team was, oh, you and Sachin are the same team.
Yes.
And which was the other team? Arunesh. Arunesh was the second team. All right, guys, I'm going to stop this. Arunesh was the first team. Okay. I'm stopping the live stream. Any questions before I stop it, guys? Are we clear about this paper? Does it make sense? No questions. Was it easy? Relatively, right? I hope.